I'm going to have a look at one of the more useful applications of, well, geometric series. It's an application of, and that's this idea of finance. Now, you may remember way back in, I don't know, year 7, year 8 maybe, when you first started looking at percentages, and we came up with this little thing called a simple interest formula, called that obviously because it simplified the idea of charging interest. Of course, this is not how they really charge interest on your bank accounts and things like that. But it was just simply, well, there's many variations of it, but one of them is PRT, where I is the amount of simple interest, P is the principal or the amount you're borrowing or saving, R is the interest rate as a decimal or a fraction. So some of you might have seen it as PRT over 100. In that case, R would be a percentage. And T, of course, is time. So here we go. Quick little question there. $3,000 invested for 7 years, 6% simple interest. How much will it be worth after 7 years? Well, we work out the interest. So 3,000.06 times 7. That's the interest. So how much will it be worth? Well, we add the interest on, 4,260. But as I say, it's a very simplistic, hence the name, simple interest, simplistic way of viewing how interest works in banking and what have you. Compound interest is, of course, how it actually works, because you get interest on your interest. And compound interest, if you actually have a look at the formula for compound interest, P is the principal, R is the interest rate, but it's 1 plus the interest rate for compound interest to the power of n. But actually look at the format of that. P times R to the power of n. What's the general term in a geometric series? AN is the amount after n time periods. P is the principal. R, and as I say, this time it's 1 plus the interest rate. And the reason it's 1 plus is because this one works out not just the interest, it actually works out the final value. And n, of course, is the time periods. With compounding, the one thing we have to be careful with, though, is that we get our interest rates and our time periods must match up. So if one's quoted as per annum, then we put the time in as years. If they compound it monthly, then we've got to put the time in months and the interest rate in months, and so on. So same question, but this time what would have happened if I compounded annually? So principal, 1.06 to the power of 7, and it's 4,510.89, as opposed to, what was the simple interest one? So obviously it's more. But if we compounded monthly rather than annually, so now the interest rate changes, because instead of 6% per annum, it's now 0.5% per month. And instead of 7 years, I've got 84 months. And we can see we get a bit more money, only a little bit, but then we are only investing a little bit. It was just $3,000 there. So $4,561.11. Okay. Depreciation is exactly the same as compound interest. Look at that, the formula didn't change. The difference, of course, is the R, because now it's 1 minus, because the value is going down instead of the value going up. And that's the only difference. We subtract the depreciation rate instead of adding the interest rate. But everything else is identical. So, an espresso machine. I believe that's a coffee machine. Don't drink coffee myself, but I'm told they're quite expensive. $15,000. Whoa! Now I know why I don't drink coffee. On the 1st of January 2001, it's going to depreciate at 12.5% per annum. What will the value of this espresso machine be in 2010? So, okay, here's our formula. So 15,000, subtract the interest rate of 12.5, but as a decimal, that's 0.875, and that's 9 years. Be careful there. temptation is to put 10 years down because we're going from 1 to 10. But if you think about it, starting at 1, then we go 2, 3, 4, 5, 6, 8, 9, 10. Oh, look, only 9 fingers. Okay, power of 9. And it's now only worth $4,500. So during which particular year will it fall below 10% its original cost? So I want to know, when is that general term going to be less than 10%, so less than 1,500? Let's solve our inequality. Log both sides, dividing by the log of 0.875, but of course the log of 0.875 is, and if we divide by a negative, we're going to have to change the sign, but if you change the sign, oh good, we're getting into it, very good. N is greater than log of 0.1 over log of 0.875. So it's going to be greater than 17.2437753 approximately. So during which year, well, it must be the 18th year, because it's greater than 17, so we're then into the 18th year, which would be 2018. But where this becomes really useful, because we've now recognised that compound interest is like a geometric series, we can have a look at a very simplistic view of superannuation. Because with superannuation, what happens is you pay regular amounts in over a time period. And then your total value then would be the sum of all of these terms, if you like. This one comes from the 2002 HSC. So here it is, a superannuation fund. It's going to pay an interest rate of 8.75%, compounding annually. Stephanie is going to invest $5,000 at the beginning of each year, commencing on the 1st of January 2003. What will be the value when she retires? Who can retire after 20 years? Anyway, when she retires on the 31st of December 2023. Okay. Well, that very first investment that she makes, that $5,000 will be, well, apply the interest rate, so 1.0875, but it'll be in there for 21 years. Okay. So, because it'll be in there for all of 2003, all of 2004, all of 2005, so on and so on and so on, all of 2023. She takes it out then. So 21 years it'll be in there for. But then the next year, she's going to make another payment. And it'll be in there for 20 years. Then the year after that, she'll make another payment. It'll be in there for 19 years. You see, we're starting to get our geometric series here. And we could keep going like that until the last one will only be in there for 1 year. And so there is our series. So to work out the value, it's just the sum of a geometric series. So the total value will be, and there is the series, 5,000 times 1.87521 and so on and so on and so on. Or if you prefer, you could read it backwards and say 5,000, 1.0875 is the first term. That might make it easier to read if you do it that way. And then we know, oh, we've got 21 terms. So I'm going to do it that way. A is 5,000, 1.0875. The ratio is also 1.0875. N is 21. So we want the sum of 21 terms. So subbing it into our formula, A, R to the power of n minus 1 over R minus 1. And there we go. She'll end up with 299,604.86. Remember, that was investing $5,000 every year for how long? It was 21 years, wasn't it? What are 521s? So you see how much money she's made. So she invested 105, ended up with 299,000. And that's the beauty of superannuation, because they're in there for such long time periods. You end up with a lot of money at the end of it. Now, there's a little asterisk here because this part of the question wasn't actually in the HSC. I've just added it in here. Find the year when the fund first exceeds $200,000. Right, so there's our series, but this time I don't know what the last term is because we're trying to find how long. So when is the sum to n going to be greater than $200,000? So again, we just sub into our sum to n formula. Fortunately, the numbers work out okay. On the right-hand side, when I play around with all those decimals, we end up with 280 over 87. So add 1 to both sides. Pretty much the same sort of questions we've been doing. Log both sides, divide by the log of 1.0875, which is a positive number. And we get 17.16, etc., etc. So, all right. We now, 2021, which would be the 18th year, is when it first exceeds 200,000. Let's try this one. This is a bit of fun. How much? Like, I want $1 million because it just sounds like a nice amount to have. So I want $1 million by that 31st of December 2020. How much will I have to invest to do that? So now I don't know how much I'm going to invest. So my series now, I know how long it's going to be in there for. It's going to be in there for 18 years. P, I don't know P. I want to work out how much I have to put in each year to get to that magical figure of $1 million. So, all right, we still know A is P, that unknown quantity, times 1.0875. R is 1.0875. N is 18. We want to know when is the sum to 18 going to be equal to $1 million. Sub into our formula, and really, it was just solving it to find P. It's actually quite a simple little equation when you think about it, because I've just got some constant times P. So I just divide by that constant. And in fractions, divide by that fraction, invert and multiply. Just got to be careful with your calculator, of course. We end up with 22,818. So, but remember, that's a year. So if she could afford to put in, well, let's say 23,000 each year, she'd end up with $1 million under these conditions in 20 years' time. So 23,000, how much is that a week? 23,000 divided by 52.
I think it's 442.
442? So that's not too much, really, when you think about it. You still have to have a reasonable wage, I suppose, to be able to afford to put $400 away each week, but it's quite achievable, quite achievable. Loan repayments is another really good use. And in fact, look, the internet has sucked the fun out of this, I've got to tell you. Because now you want to take out a loan or something like that, they've got all these loan calculators, and all you do is punch in the numbers and it tells you, oh, you can afford to borrow this much, or this is what your repayments will be, and these sort of things. And it does all the number crunching for you, so it's taken all the fun out of it. I used to do it longhand before all the internet came along. So when I wanted to work out how much I wanted to buy my first car, and I'd create the geometric series and work out and all that. Well, that's all the calculators on the internet are doing. It's just creating the geometric series and doing exactly what I'm doing. So this is how we work it out. The amount still owing after n time periods is, if you remember this idea, you can't go wrong. The amount remaining will always be the principal, so how much you borrowed, plus the interest, minus the instalment, so how much you paid back, plus the interest. Okay. Richard and Kathy, named after two friends of mine, actually. I was in the bridal party at their wedding. Yeah, they're interested, in case you're wondering. But anyway, that doesn't matter. They're going to borrow $20,000 from the bank to go on an overseas holiday. Interest is charged 12% per annum, compounded monthly. They're going to start repaying the loan 1 month after taking out. When you take out a loan, you don't repay straight away. That would be stupid. Because that would be like saying, the bank goes, here, have this money. Now can I have some back? Doesn't make sense. So there's always one time period before you start paying back. And it's going to be $300. $300 is going to be their monthly instalment. how much will they owe the bank at the end of 6 years? Okay, so that initial loan will be borrowed for 72 months. Notice they've said 6 years. I've changed it to months because it's compounded monthly, and also monthly instalments. So there's a good reason for this to be all in months. Now, this is what you've got to keep in mind. Repayments are actually an investment. Okay? So when you start repaying a loan, you are actually investing money. And so that's why we apply the interest on our investment, because it's like saying to the bank, I'm going to give you this money for however many years until the end of the loan. Okay? Because they are giving you $20,000. And basically the idea is they're going to give you $20,000 and they say, I want that $20,000 back in, how long was this one for? 6 years. In 6 years' time, I want that $20,000 back. Okay? So that's the deal. And obviously they're going to charge me interest on that. And that's why I work out the total amount of interest for the 6 months. Okay? But then I say, yeah, that's fine, but I'm going to give you some money and I want the same interest rate. And so they've given me money and I have to pay their money back with an interest rate, but then I'm going to give them money. And then hopefully at the end of the time period it all balances out and neither of us owes each other any money. So my first repayment will be invested for 71 months. So it's like saying I'm going to put $300 in a bank account. Because I could have done that. Instead of giving it to the bank, I could have said, no, I'm going to put it in a bank account and I would earn this money and then I'll give it to you. So it's the same sort of idea. Instead of doing that, they cut out the middleman and said, well, if you're going to give it to a bank, you may as well give it to us because we're a bank, and do it that way. It'll be in there for 71 months though, because remember, you don't pay the first one back until after the first time period. Then I'm going to have a second repayment, but it'll only be in there for 70 months. And so on and so on and so on. The second last repayment will be there for 1 month. Because the last repayment, there's no interest applied to the last repayment because you're done. So they don't charge any interest. It's like, here, I'm giving you $300. We're finished. Contract's over. So no interest is applied to that last one. Yeah? So, principal plus interest minus all of those instalments plus interest. So the total amount owing, there's my principal plus interest. That's how much I owe the bank, minus how much the bank owes me, leaves the balance. Well, the second one, you'll notice, there's our geometric series. First term's 300, ratio 1.01, number of terms 72. So we can put it into our sum to end formula. And after a bit of calculation, there we go. So there's still $9,529. So the question is, how much interest have they paid in those 6 years? Total repayments were $21,600 because for 6 years they've been paying $300 every month. So they've given the bank in total $21,600. However, they've only paid off $10,470. Because remember we're saying there's still $9,529 to go. The original loan was $20,000. So they've reduced the loan by $10,470. So I've given them $21,600, but the loan's only been reduced by $10,470. That difference must be the interest that I've paid. That was the cost of the loan. And so that difference is, there it is, $11,129 I've paid in interest after 6 years. Quite a lot when you think about it for a $20,000 loan. But then the interest rate was reasonably high. Got to change the problem a bit now. What about if it was, like I was saying before, back in the old days, where I want to work out how much I pay to organise a car Yog. Yog, named after a student I taught many years ago now. Yog Chopra was his actual name. Anyway, buys $30,000 to buy a car. And in fact, these details are the details for a car I bought once and had to work this out. So $30,000 to buy a car. I wanted to repay the loan, or Yog wanted to repay the loan in 5 years, so 60 equal monthly instalments. Interest at the time was around, I mean, I've rounded a little bit to make the maths a little bit easier, but 9% per annum. 9% per annum. How much should it be? Okay. Now, I don't know how much you're going to pay yet because this is what we're trying to work out. So let's say it's just M for monthly repayment. The initial loan will be over 60 months. So I know this is how much I owe the bank. 30,000, 1.0075 to the power of 60. First repayment will be in there for 59 months. Second repayment, 58 months. So on and so on and so on. Second last one, 1 month. And then the last one, of course, is in there for no months. So I give them the last repayment, we're done. Amount owing will always be principal plus interest minus instalments plus interest. So amount 60 will be 30,000, 1.0075 power of 60 minus that particular series. Okay, well, that series, A is M, what we're trying to find out. The interest rate, or R, is 1.0075. N is 60. There's our formula. Substituting into our geometric formula. But hang on a sec. We know what amount 60 is. It's going to be 0, because this is when I pay off the loan. So now I can solve this equation and work out what M is. So all of that has to equal 0. Don't let the big numbers scare you. So rearranging, all we're doing is trying to make M the subject. So I've just got to move that first term over to the other side, divide everything by the coefficient of M. There it is. Obviously, we need to go to a calculator and make some sense out of this answer. And that amount works out to be $622.75 a month is how much we'd need to pay back. And as I say, back in the good old days, that's how I'd work out whether I could afford the loan or not. All right, what about if it's something different then? How about I know how much I can afford, how much I want to borrow. I want to know how long is it going to take me to pay this loan off. Okay? So how would I find the length of the loan? This is an HSC question. Wheelbarrow back, Shire Council, borrows, that's a lot of money, $3 million. But they are a council, so okay. Beginning of 2005, annual interest rate 12%. Wow, that's nice, seeing there's 12 months in a year. Ooh. Each year, interest is calculated on the balance at the beginning of each year, added to the balance owing. The debt is repaid equal annual repayments. Oh, they could have made the interest rate anything, couldn't they? We're not doing per month, so what does it matter? Let amount N be the balance owing after the nth repayment. So, show that. Amount 2, so the amount left after 2 years is that particular expression. So, okay. Well, we know the initial loans borrowed for 2 years, 3 million, which, by the way, in scientific notation is 3 times 10 to the 6. First repayment will only be invested for 1 year now, because we're only talking about 2 years. And then the second repayment, 0. Power of 0 for this one. And so it'll be principal plus interest minus instalments plus interest. So, and we actually have got the same thing. The only difference is they're using scientific notation. I've got a bit of factorising to do on the second parentheses there. But if I factorise that out, we have got the same expression. Show that amount N is this wonderful expression, 10 to the power of 6 outside of 4 minus, okay. Well, this time the initial loan will be to the power of N, because we don't know what N is. So the first repayment will be for N minus 1 years, then N minus 2 years, and so on until we get to that last repayment. Still the same idea, principal plus interest minus instalments plus interest. So subbing in, there's amount n, but we want to show it's 10 to the power of 6. So we've got a bit of work to do here. Let's play around with our series. The first term is, well, you can do it two ways. I've factorised the 480,000 out. So you could, if you like, say first term is 1. I've still said it's 480,000. Doesn't really matter, because however you do it, you still get A outside of R to the n minus 1. So whether you factorised it out or you left it in there, you'll end up with 480,000, 1.12 to the power of... Okay. Boy, now we know why they gave us 12%. 480,000 divided by 0.12. Oh, that worked out nicely. That's 4 million. So that went in quite nicely. And if I expand that out, now I've got, oh, look at this, I've got two terms with a common factor of 1.12 to the power of n. So that becomes 4 million minus 1 million lot of, well, let's factorise the million, and we have the expression that they were looking for. Very tricky question for 2 unit, that one, actually. So the last question, I think this is the last part of it. What year will they make that final repayment? So when is a(n) equal to 0? So all we've got to do is solve this equation equals 0. And we'll come up with, eventually, log 12.23 years. So 2017 in this question. Okay, look, I've only picked a handful out of each one.